All right. JS Conference, hayas tanım. Dızets. Ayo. Welcome, everyone. I'll be giving my talk in English, but if I speak too quickly or say something you don't understand, please let me know, and I'm happy to explain it again, even in Armenian if I have to. I'm Rouben Meschian, and this talk is about optimizing for correctness. And what do I mean by this? So it turns out that programming is complicated. Don't know if you know that yet, but it is. Douglas Crockford says that programming is the most complicated thing that people do. The most complicated thing that people do. How does he back up this claim? Well, he says something very simple. You see, we have a contract with the computer that says this. Our programs have to be perfect for every scenario, for every input, for every possible state. And if our programs are not perfect, the computer has license to do the worst possible thing at the worst possible time. That's bad. And the problem is humans are not good at perfect. Right? And the other problem is there's no measure for perfection in programming. Like there's no test you can run that will tell you your program is now perfect. Remember, tests don't tell you about non-existence of bugs. They only tell you about existence of bugs. So this is a problem. And back in the day, mathematicians were thinking, okay, maybe we can solve this problem mathematically using the discipline of mathematics. And there was a whole field called proof of correctness. What is proof of correctness? Proof of correctness is attempting to use mathematics to make mathematical proofs of programs. This failed. I'm guessing you know why. Because the proofs that they were creating were actually more complicated than the programs they were attempting to prove. So that didn't work. So what do? We're trying to do something that is very complicated, but we're not good at meeting perfection. So what can we do? Well, it turns out the best we can do, in addition to testing, is to minimize complexity. The more complicated our programs are, the more likely they will have mistakes. I think this is simple. Now, what's interesting to me is that when programmers are coding, or when managers of programmers are sort of managing different tasks, the things that they seem to be optimizing for are very often not the right thing. Remember the fundamental principle of optimization, of any kind of optimization. You measure, then you optimize and you measure again. And you make sure that the optimization that you made a difference in the measurements, right? People often optimize for little things having to do with development. Keystrokes, minimizing keystrokes, optimizing hotkeys. You know, did you write your code in 3 hours or 2 hours, right? It turns out that most of the time that you're spending is not in building stuff. Building, coding, just writing stuff is the fun part. It's the part we all love to do. But that's not where you're spending a lot of your time. You as programmers are actually spending a lot of your time reading code, debugging code, trying to figure out what the heck is going on with your system. You're actually spending way more time doing that than just merely writing code and doing fun stuff, right? This is why we get paid, by the way, is because we do all that complicated stuff. So what we need to be doing is optimizing to minimize that bigger piece. So how can we do that? Well, we need to optimize for correctness. Our goal shouldn't be to write code quickly, it should be to write code correctly. Again, because in the long run, if you have code that works correctly, you will actually save yourself a lot of time in debugging and adding features, etc. So, what can we do to optimize for correctness in our code, to make sure that our code actually works as expected? Well, we all understand that as you begin to program, you realize that a lot of the decisions that you made earlier on were actually wrong. They no longer apply to the current system because the system has changed so much. And so the thing we have to do all the time is refactor. I've seen companies that will refactor as part of a sprint. Like in this sprint, we are refactoring. No, you refactor all the time. Every time you get code and you're writing code, you're going to see things that no longer apply. Don't wait for later when you will have an official sprint scheduled for refactoring. Refactor then, right at that point in time. You should be constantly keeping your code clean and everyone else's code clean, by the way, as you're moving forward. But a question arises, why do people not do this? Well, sure, some of them are lazy, that's one reason. But the second thing is they're worried about breaking the system. They're worried about introducing bugs, which is a fair point. But we have a mechanism to defend against that. That is known as automated testing. Automated tests are there to do exactly this. They're there to make sure that the promises that your code created to the rest of the system are kept over the course of your software, or as the software is modified. If you have tests to assert that the promises that you made are true, even when you modify your code, when you move things around, you will make sure that the changes that you made did not negatively affect the system. And so one of the reasons why I'm always surprised when people say, we're too busy, we have a short sprint cycle, we don't have time for tests. Think about what that means. If you don't have time to write tests, then you can't refactor moving forward. You're not optimizing for the right thing. You're optimizing for the short sprint, for the development cycle, not for the long haul. In the long haul, if you don't refactor and keep your code clean, your code will get nastier and smellier, and it will be much more difficult to debug. Remember, the messier your code is, the more bugs you're probably going to have because it's more confusing, it's more complicated. Furthermore, as you move forward, it's going to be more difficult to add features to your program because your code will just get dirtier and dirtier, and things will just stop making sense. And just like many other companies, you're going to have to say, stop. We either have to refactor or rewrite the entire thing because it's a big smelly mess. So we need tests, absolutely. But here's the thing. It's not always easy to write tests for code. Code itself has to be written in a way that it's easily testable. What do we need for code to be easily testable? Well, think about it. Code needs to be able to run the same way over and over again for you to make sure that when you run it again, you get the expected result. That is to say, your code must execute deterministically. You need deterministic execution. So, let's take a look at a piece of code. Don't worry about what language this is in. It's a language I actually made up, to be honest. But, so the first line of code, you have x plus 1. And I'm here to tell you, to guarantee you, let's say, that b would be a 2. You got it? b is now 2. First line means b is 2. Then you print the x plus b. But what you get is something like 22. Does that make sense to you guys? It does? Who does it make sense to? No, I mean, like, how can you, what does x have to be for b to become 2? 1. So how is it that adding 2 plus x returns 22? Logically, it doesn't make sense, does it? And you might be wondering, well, how is that possible? Consider this scenario. We have a thread of execution. This thread has some resource, in this case x equals 1. And what this thread will do is it will spawn 2 additional threads. For those of you who are still sort of getting into computer science, thread of execution, just imagine when your code runs, imagine more of that. Like at the same time, your process has a bunch of things running, executing kind of at the same time. And I say kind of because it depends on how many cores you have. If you have one, then a little bit of one runs and a little bit of the other one runs. If you have multiple cores, then you could actually literally run them in parallel at the same time. Okay, so you have parallel execution here and you have parallel execution there. And in this code is where we have the code that I had in a previous slide. We have the b equals x plus 1 and then we print b plus x. In this code, after running some code, at some point this thread decides x should be 20. Fair enough. And it just so happens that just because of the way the 2 threads are scheduled, that this happens to run right in between there. Right between that and that. And this is a problem that happens when you do multi-thread programming. In fact, one of the biggest complications in writing multi-threaded programming is exactly this, is when you have shared mutable state. Shared, as in both have access to this resource. Mutable, because it can be modifiable, it's not a constant. And it's a resource. Okay. So this is a problem. And we'll get back to this in a moment. Now you might say, wait, threads? We're JavaScript programmers. Why are you talking about threads? We don't have threads in JavaScript. We don't. Well, we'll talk about web workers later on, but for now, let's just say we don't. Let's abstract that out. Consider this scenario. This is actually JavaScript, okay? So in this case, we have a mutable resource, in fact, a shared mutable, as you will see in a moment. We run that code that we ran, the first line of code, right? B equals x plus 1, fine, and we get the 2. Then we call two asynchronous functions, right? So we call do something and do something too. Both of these are asynchronous. And let's just say for a moment that both of them will cause an AJAX call to the server, okay? So an AJAX call goes out to the server, it comes back, and it just so happens when this one comes back, it prints b plus x and changes x to 100. If this one comes back, again it prints b plus x, but it changes x to be 10. Here we have what is known as a race condition. In a race condition, you have two things that are racing to do something. One might happen, but the other one might happen. The execution of this code is potentially non-deterministic. It does not happen the same way each time. If these were in fact calls to the server, it's entirely plausible that this call might go to the server and the resources necessary to execute that service might be readily available. This runs very quickly, this runs very slowly, this comes back before this. But the opposite might happen, right? The resource necessary to run this might be busy, this one might be free, so this one runs immediately, comes back, this one takes a bit more time. This is an issue. Now, one thing that all of you may potentially be asking yourselves is, but why are we changing x? And if that's what you're asking, you're on to a good start. This is a piece of code that one of my students wrote last year. They were asked to write the factorial function. We generally first begin writing factorial using recursion, and then I teach them about mutation. And so here they are writing a for loop. This program is sort of correct, right? So first of all, but many of you are noticing that there's an issue here. One is that it's only correct the first time you run it, right? Because after that, result ends up being modified, right? In this case, you have a result that is outside of, by the way, for those of you who don't know the syntax, this just means there's a function here that takes n as an input, and this is the body of the function, okay? So we have a variable here called result that's set to 1, and then we have a function that will iterate over from 1 up until that value, the value that you give it, the input, multiplying this result by that number. Therefore, you get factorial, 1 times 2 times 3 times 4, blah, blah, blah. Okay, the problem though is, first of all, this code is actually incorrect. And it's incorrect because if you call it one more time, the result of result will be not 1, but whatever the last run was, and so you'll keep multiplying on top of that and get something wrong. And so, okay, we could fix that easily. We could potentially reset result to 1 each time. So now this code is actually correct. But is it good? Is it complicated? And is there anything we could do to make it less complicated? Now, all of you who have some experience programming, look at this and right away there's like an ick, right? There's something wrong with this. This is not the way you would do it. But let's really understand why that's ick, right? Why would you not do that? Well, first of all, remember that result is no longer inside of factorial. Because it's not inside of factorial, that variable is not owned by the factorial function. It's outside. It's available to others. Other code that might be running here, or maybe there, or somewhere else has access to result and can use result. Why not? It's in their scope. Why should they not? But the problem there is, imagine how complicated it would be to write code against result where every time a factorial gets called, result changes underneath you. All right? Think about that for a moment. Depending on when factorial is called and by what value, that will determine the value of result. Now try to imagine writing logic somewhere else using result with that situation in mind, where the value of result can change all the time depending on whether factorial is called, when it's called, and what value it's called by. What I just explained to you was a needlessly complicated scenario that could easily have been avoided. How can we avoid this? Well, we could do this. Why leak our internals out into the system? If we have resources that we need to use, okay, use them, but use them internally. Don't leak them out. The complication that arises there is very simple. When you leak a resource out, others have access to it. It's now a shared resource. And now others could now be using it and get confused by it, especially if you modify it. So, 2 lessons to be learned here. One is to minimize the scope of every variable that you make, right? Seems reasonable. Every time you make a variable, have it live in the smallest possible scope. This is good for the scenario that I just described, but there's another reason. Because the smaller the scope, the easier it is to reason and to understand about your variable. If you just imagine you have a global variable. Try understanding how that variable is used in your system. How can you do it? You have to literally look at your entire system because your entire system, by definition, has access to that variable. One of the reasons that makes creating global variables a bad thing. So localize your variables as much as possible so that when you're trying to reason about your program, whether you're debugging or you're trying to understand it, you only have to understand this much to understand how the variable is used. Not that. Make sense? Okay. The second part, something else that you might have noticed, is that when a function runs, it could, while it's running, go change something, right? Imagine you call a function and it's like, okay, like that factorial function. We called it and it said, okay, here's the factorial, but it went and changed this other variable that is shared by the rest of the system. That's weird. And one of the reasons why that's kind of weird is because when a function just changes something like that, in order to know that it changed, you either have to understand that that's the behavior because it has to be well documented and so on, or you have to read the code. Calling factorial did not tell us that result was going to change, right? Factorial is supposed to give us a factorial, not change something out there. Changing something out there is a bit weird. So there's a notion in functional programming called side effects. Functions should avoid having these side effects. A side effect is when a function, other than just returning you a value, goes off and like modifies something over here. Modifies something on the side, has a side effect. Okay? In your systems, you should minimize side effects. Now, why do I say minimize? We just saw how horrible a side effect could be, right? You call a function, it modifies something over here, and it screws everything up. But sometimes you actually need side effects. Every time you write to a database, that's a side effect, right? That's not just a function returning to you a value. That's a function that goes off and modifies something over here. In this case, this thing over here is the database. So yes, I accept that sometimes in your programs, your functions have to have side effects. But keep that to a minimum. One of the things that I'm going to be talking to you about, functional programming, which I'm kind of easing you into, functional programming is an approach to programming. It's not a solution. It's not a religion. It's not like everything in your code must be this or you're a horrible programmer. This is not what I'm telling you. What I'm telling you is treat functional programming as an approach. Think about it. Every time you guys sit down to write code, you are creating something new. You are writing code for the first time in that way, okay? You might be building yet another, I don't know, content management system, but I guarantee you the way you're building it, your code is going to be different from every other content management system out there. Even if you haven't innovated or creating anything new as far as features go, your code, your program, the thing you've actually produced is very novel. So you're constantly creating something new. Well, the question is, when you have a blank sheet in front of you, when you just have a blank editor in front of you and it's time to just write code, how do you approach that? One of the things that my students always ask me is, how do I structure my code? Like, how do I know where I should put the if statement? How do I know where I should put my variables? Functional programming attempts to guide you in that direction, ideally in a positive one. And so we'll see more examples of this soon. The other thing, so we talked about sort of shared variables, right? So variables that can be shared across lots of things, and we talked about how functions, when called, should ideally not go off and modify them, right? That would be a side effect of that function. Okay, but what about local variables, right? So we talked about shared, variables, but what about variables that are literally in the function that we're talking about, such as the factorial function, right? What about them? Well, let's talk about those. What does this mean? Well, what this means is that x is an identifier. X is an identifier for O. If you see x in the program, it's O. You can sort of replace it in your mind. Reasoning about that, fairly straightforward. So O is a value that is assigned to x, and x is an identifier of O. Simple, no problem. Here's where we fall into some problems. What this means is that x is no longer an identifier of a value. X is now a state, and that state can change. Much more complicated to reason about. Why? Well, let me explain. Because in order to now understand what x is, you can't just say, okay, x is 0. No, x is depending on what happened before. The problem with changing state, which is what we're doing here, is that introduces the notion of time. The value of x before you run this code is different from the value of x after you've run this code. So what that means is that when you're reasoning about a variable, when you're trying to understand its value, it's no longer good enough to just read it, which is what you would do with x is O. You now have to read through your code, potentially go through some deep nested if statements to then try to understand, oh, in this particular case, the value of x would actually be something completely different. And so this adds an additional complication to your code. And so something else we could do is, if you want a different value, why not have a different variable? Sounds reasonable. Why don't we try that? So what is this? This is the exact same factorial function written in a way that a variable does not get modified. Okay? So this is a recursive function. And in this recursive function, you can see no variable is getting modified. New variables are being created. Every time the factorial function calls itself, the new function has new variables created inside of it, yes. But no variable is being modified within the context of the function itself. That is to say, each variable is now immutable. It does not get modified. It is not mutable. By the way, with a little bit of syntactic sugar, the factorial function can be written that way, with a ternary operator and using the new function thing. Kind of cool. So we just changed that big thing with the for loop and all that junk into something much more terse, much more simple, much more short. And nothing is modified here. Let's continue. So what happens when we run recursion? Let's break this down a bit. So in this case, so let's say we call, factorial with a 5, okay? That function then that call then calls a function. So these big blocks are functions, and these things are function calls within the functions. So this is a function, and what would happen is you would say 5 times, and then you would do another recursive call, boom, which would then do 4 times another recursive call, boom, and you'd keep doing this until you hit your termination case, which is 1. And then that function would return a 1. This would return a 2. This would get replaced with a 1. You would do 2 times 1 and come here, boom. Then 3 times 2 would get returned here, 4 times 6, 2 times 4, 24 times 5, and then you get 120 as your answer. So it's sort of things come returning back, okay? Okay, so that's recursion. We all know recursion, nothing new there. What happens with memory when you're doing recursion? Well, there's this data structure called a stack, which some of you might have studied. And what we do is a stack is used to hold the variables of a function. Okay? So each time you go into a function, all of the variables for that function are pushed onto the stack. So in this case, let's consider this scenario again. When you make a function call here, this function has a local variable n, which is represented right here. So this is the memory that is allocated for the variables of this function call. Then this function calls that other function. So the memory for the other one gets added and pushed onto the stack. Then the next one, then the next one, then the next one. Then when this function finishes and returns, the values, the context, all this information about that function gets popped off the stack. And so as you return, the things just get popped back off the stack because you no longer need them. Once you return from the function, you no longer care about the variables of that function. You can forget about them. You're done executing that function. So as that happens, as you return, these things get popped off the stack. Fair enough? Now, what happens with recursion? Well, imagine if you don't do a factorial of 5. Imagine if you try to get the factorial of, say, I don't know, 1,000,000. Well, you would have to do a function call after function call after function call 1,000,000 times. So what happens? Things keep adding to your stack. And what you get is what's known as a stack overflow. StackOverflow.com, our favorite website. That's what a stack overflow is. So it's when your stack gets full of all the stuff and then there's a limit to this memory. This is not infinite. This is finite memory. And so as you keep adding to the stack, eventually you can reach a limit. And that limit will be met very easily in the browser, and too bad. So recursion is a problem. But there is an optimization. It's called a tail call optimization. And what do we mean by a tail call optimization? Well, before I explain to you that, consider this version of a factorial function, right? What is the last operation that happens when a factorial returns? Not this one, forget, okay, it returns a 1, I get that. But suppose this if statement fails. What is the last operation that happens in this function? The multiplication. Look what happens. We have the n, okay, we have the n, there it is. But we don't have the result of this. So we must first resolve the result of that to then multiply that times that. Make sense? Therefore, multiplication is the last thing that happens. So why do things get added to the stack? Well, the reason they get added to the stack is because when you go off to try to compute this, you can't forget about that. You have to remember the value of n so that when this function returns, you can then multiply the value of n times the result of getting that function. Okay? So you have to keep the information about this function around in order to run your multiplication. In a tail call optimization, what we mean by this is as follows. Suppose that was not the last thing in a function. Suppose the last thing that we did in a function is call a different function. The last thing we do in your function is call another function. In that case, when that other function returns, is there anything else that we're doing? No, because that was the last thing we did, is call the other function, right? Okay, well, if that's the case, then why are we remembering all those variables? There's no need. So what we can do is when that function is called, we can actually remove all this information from the stack and just worry about the function you called. Thereby not overflowing the stack because the stack keeps getting things removed from it as you're recursing. here's a modification of the factorial function that I did, which would result in a optimization, in this tail call optimization. Sorry, not this one. Sorry, not this one. This one. Okay. So in this case, what is the last thing you're doing? You're calling a different function. So why do we have to remember the value of n or the value of ac? Ac standing for accumulator. There's no reason. So we can just pop all this information off the stack and just worry about this one. And then the next iteration, again, we pop everything off the stack and just worry about the next layer, and the next layer, and the next layer. And at some point, when we reach the end of it, we just return that as the value. And by the way, as far as optimization goes, as far as speed of execution, this can run just as fast as a for loop. Because if you think about it, what is a for loop? There's some condition. You have local variables within, you have block level variables, right? It's block scope. So you have local variables there. You do some execution, then there is a jump up to the top of the for loop, which then re-executes everything. This happens exactly the same way. You execute a function, then there is a jump to the top of the function, executing it again, and so on and so forth. Right? Okay, so tail call optimizations are pretty cool, and they can allow us to do recursion without worrying about Stack Overflow. But there's a problem. It is not yet available to you in browsers. I said all this just to say, guess what? You can't use it. You're welcome. So we can't take advantage of tail call optimizations yet. Although, from what I understand, they're planning on adding it at some point in the future. Okay, so what do we do? Well, think about when you wrote your last loop. So recursion is used for looping, right? It's a cyclical thing, and it's the only way we know to loop without modifying variables. Now think back to your programs. Most of the looping that you did, do you remember why you did them? I guarantee you, because I did a study of my own code, and I wrote a lot of code, and most of the time when I do looping, I do it for the same reason. I'm iterating over an array. I've had very few loops where I'm doing other things. Yeah, sometimes I'm doing some, operation that wants to repeat or something. But most of the time, I'm iterating over a list. For loops. I want to talk about these for loops. Do you guys remember die? Who remembers die? What does that stand for? Duplication is evil. Remember that? You were taught that. Repeating code is a bad thing. Why is duplication of code a bad thing? Why is it bad to just copy-paste code? Because later, if you find that that code has problems, you modify the code, you still have a problem. Simple, right? So duplication is not a good thing. The other thing, it leads to bloat. Your code base becomes bigger because you're duplicating the same thing over and over. We know this is wrong. All of us know it's wrong, and yet we do it all the time. But how is a for loop duplication of code, you ask? We do it all the time. It's like the second thing we learned in programming class. Look at the code. You make a variable. You make a condition. You change the variable. You do 3 explicit operations minimum every time. That is a duplication of code, guys. You are re-implementing the mechanism to cycle over an array. I found this out a few years ago, actually, when I read an article about this. The article said that rather than checking the length of the array every time, instead what you should do is you should store it as a variable and then check the variable. Because running looping over a large array this way is actually faster than this way. This article was written about 2 years ago. Engines might have changed, various optimizations may have been added. This may no longer be true, but that's not the point. The point is, I read this article and I thought, hey, that's awesome. I should totally go and change my for loop to be this. And guess what I had to do? I had to go through all the different for loops, changing each one at a time. Yeah, I did some intelligent regexes or whatever, but at the end of the day, I was modifying the same thing, the same kind of code, all over my code. Hundreds of potential iterations of this. This is a sign, a clear sign of code smell. If you have to go through your entire code base, changing things everywhere, the same thing, that means you have duplicated code. Duplication is evil, guys. We do not duplicate code. Avoid duplication as much as possible. So, what do we do if we notice that code is duplicated? We encapsulate it. We make it reusable. We abstract the complication of that program away, and we reuse it. And then if we want to change it, we want to modify it, we want to fix a bug, we just change it. We don't go around and change everything else. The implementation is abstracted away and encapsulated in a reusable function, potentially. So, let's do that. Instead of constantly writing a for loop everywhere, we could have written this. A function that takes an array, takes a function which will execute as far as the body of the for loop, if you will, and then put all of our for loop information here. Now if you want to optimize your for loop, if you want to add a dot length or you want to do whatever, you just do it in one place. No problem. You get another benefit. By using now this function, you are no longer modifying a variable as you're iterating. You're modifying here internally, yes, but at least you've minimized it to just this one place. You're no longer modifying variables and re-implementing a cycle everywhere in your code. You've now brought that complexity down to just this one function, and you can reuse it everywhere in your code. Kind of nice. Now it just so happens, and everyone can be very happy about this, that there are native implementations of for each attached to the prototype of the array. So, for any array in your JavaScript execution environment, assuming you're using a modern browser, which I know all of you are, you can just do .for each. And the complication, the code that is necessary to iterate over the values of that array, are abstracted away from you. All you care about is that you give it the function that will get called for each value within that array. Kind of nice. And that function, by the way, also we could have written this using the new syntax with the arrow function, takes a value and the index. Okay. Well, it turns out there are additional ones. Suppose you wanted to transform your array. You have an array of numbers, and you want to create another array that has the same numbers, but where each number is one more. So if you get 1, 2, 3, you want to get back, 2, 3, 4. For transformations, we use a map function, which works very similarly to for each, but you return the new value for that index. That's simple. So in this case, if you get an array that has, let's say, 1, 2, 3, well, 1 will get passed here. You will do 1 plus 1 and return a 2. So the first index of the new array will now be a 2, then a 3, then a 4, and so on. And you could use this to do all kinds of transformations. You could take an array of objects and turn them into strings. You could do whatever, right? It's a very useful mechanism. By the way, how am I on time? I don't have a watch. Okay, all right, whatever. Okay, the other thing is filter. Kan det stå? Ah, cool, I have lots of time. Okay, the other thing is a filter. Why a filter? Well, it's very common when you have a list of things that you want to pull some of them out. Okay? So you have a list of, I don't know, university students, and you want to get all the university students whose first name begins with A. Okay? So what you would do is you just do that array, the array of university students, dot filter, and here you just check that that value, which is the object representing the student, the first name of that object begins with A. This returns a Boolean value. If the Boolean value is true, that student will be added to the new array. If it's false, they are not. What's important to note about each one of these functions is that none of them will modify the original array. They will return, map and filter will give you new arrays. They will not modify the original array. So if you do map, you're not modifying the actual array, you're just getting back another array that is the transformation of the original. Same thing with filter. So This is good. We're not mutating anything, so we're keeping within the realms of functional programming. In JavaScript, we now have const. It's important to understand what const is in JavaScript, because a lot of people get confused with this. In JavaScript, const does not actually mean constant. What I mean by this is it doesn't mean that the value is constant. What const means is that the reference that you're making, the assignment, is constant, not the value. Now, for literal values, we're not storing references, we're storing direct values, so no problem. Here we can have const a is 1, and you know that a will always be 1. It doesn't matter when you call it, doesn't matter how many conditionals you have or for loops, a will always be 1. No problem, that's easy. Same thing with strings. Strings are immutable, so you can just treat them just like regular primitives, and then booleans as well. Fine. But, and here's where a lot of people get confused. What does this mean? What this means is that P1 now has a reference to this object. It doesn't mean that this object is a constant. No. It means that the reference from P1 to this object will always be true, will always be that. The assignment is constant. In other words, you can't then later say P1 should now be 5. You can't do that. You can't change what P1 is assigned to. But you can change the value within this object. Okay? So this is a problem. So how do we get immutability? Well, there is a function called object.freeze. What does object.freeze do? It freezes this object. Okay? What does that mean? What that means is that later, if you try to modify the name, it won't let you. I don't want anyone here to use this function. Let me explain why. If you have a constant, and you try to change what that constant is assigned to, in other words, if you go here, go there, and you change a here to, a 4, what will happen? If you then, after doing const a is 1, you then say a is 2, what will happen? Error. You get an error, okay? And you, as you're coding, will immediately realize that you made a mistake. In fact, you could even have a compile time error, right? If you're using some sort of compilation or some other tool, like a linter or something, they can identify these and tell you before you even run your code, right? Okay, so that's good. Good. Errors are actually a good thing because they prevent us from making logical mistakes. In this scenario, and I've tried this, the problem is that there are no errors here. When you do this, it says, Hajana, no problem. Name is now Mike. It doesn't change name. And so people get confused, right? You say, but wait, this ran, then the next line, then the next line, and then I'm assuming that p1.name is Mike, right? But it's not, even though it allowed me to do so. So it allows me to make the attempt, doesn't give me any errors or indication that it failed, but guess what? It failed. So, in my opinion, this will cause more confusion than actual mutation of the damn thing. So, avoid using object.freeze, even though I think the idea was good. I think if it caused an error, this object.freeze would be an awesome function. But right now, when I use it in Chrome, it just allows me to do this, and then just doesn't do it, which is weird. So, for now, avoid doing this. So, how do we deal with objects? Well, through programming discipline. So there is object.assign, which is actually, for those of you who have some jQuery background, the same thing as extend function. Dojo had mixin. The idea is very simple, that each property or each attribute of an object can be copied into another object. So consider this. We have a P1 which has an object with name and age. We can then do object.assign, giving it an empty object. This first object is what will eventually be returned and assigned to P2, okay, eventually. But before that, every attribute of P1 will get copied into this object. In other words, name, Joe, age 18, will now get copied into that one. But here's the thing. The next object is then copied over the top. And you can have as many of these as you want. And it will copy this object, then it will copy this object, then it will copy that object. In this object, we said that name is Mike. So what happens? Well, this object takes on name Joe, age 18, then this copies name over this other name. And so the object that we end up with has name Mike and age 18, right? So in this way, we can take all of the things from the original, mix in all the changes that we want, and end up with an entirely new object that is completely distinct from this one. And now, if any changes did happen here, it would not modify the original object. With me? Cool. One thing to note is that this copying is not deep. It's a shallow copy. It only copies the immediate attributes of that object. If you want a deep copy, like if you have a nested object which may have nested arrays and so on, you need to use a library. And there's things like deep merge and other libraries and functions that exist out there that you can use that basically do this, but do it recursively. So, what about arrays? There are certain functions associated with arrays that will modify the array. Push modifies the array. Pop modifies the array. Setting something to an index modifies the array. Attempt to avoid these mechanisms. Instead, we have concat. Takes two arrays, returns a new one. We have slice. You can take any part of an array and get it back as a separate new array. Does not modify the original at all. And then we talked about filter and map. Filter to remove things from an array, that is to say to get a new array minus whatever you didn't want. Or map to transform the array if you choose to. With me? Now, let's talk about memory. A lot of you are thinking, wait, you're doing all this copying, right? Every time you're copying an object, what if that object is large, blah, 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 right? I mean, you can see that there's a use of memory. There's a penalty of memory when you're trying to do things in a functional way. Fair enough. May I remind you, first of all, that memory is now fairly cheap. I found this on Amazon. It's 1 terabyte of memory for 30 bucks. A terabyte of memory, guys. That is a crap load of memory for 30 bucks. So it's not like memory is a problem. In fact, back in the day when memory was a problem, people, yes, you're right, they used to make one variable and they used to reuse it for everything. And they knew where like the registry and where everything was, and they were like super optimal and careful. But guess what? The code that they wrote was very complicated exactly for this reason. Now we live in an age where memory is much larger and much cheaper. Making this optimization no longer makes sense. It's now much, again, remember, optimize for the right thing. Optimizing for memory versus optimizing for correctness. I'll go for correctness. Now again, I'm not suggesting that memory is never a problem. If you write a horrible algorithm, it can consume memory, of course. But what do you do then? Write your code correctly, write the unit test for it correctly, get everything to work, then make the optimization. Again, I go back. How do you make an optimization? You measure. You measure how much memory you're using, determine that is the bottleneck of your system. Interesting point. It may be consuming a lot of resources, but if it's not the bottleneck, that is not where you should be spending your time. Because even if you optimize that, you're not optimizing the overall performance of your system because something else is still slowing everything down. So, don't worry about premature optimization. Don't try to optimize your code ahead of time. I'm not suggesting you should write crappy code. You should still think about what you're doing. But this kind of optimization, like, I don't want to make another object, that might use too much memory. Guys, that's a micro optimization that in the long run probably will not matter. Second thing to note. Remember, Edgar actually mentioned this earlier. Remember how I was saying that you should try to localize your variables as much as possible? Well, if you're making your new objects, but you're making them locally, What happens once you get out of that scope? You very often lose a reference to that variable, right? You're no longer using that variable. What happens when we're no longer using an object? Garbage collection. It gets removed from memory. It gets freed from our memory. So even though you might be, yes, allocating memory more often, but you're also you're getting rid of that same memory immediately. You're running a function, yes, you're creating objects, blah, 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 and then you're returning, and all of that just gets garbage collected. So actually, in the long run, you may not actually be using as much memory as you think you might be. And in Edgar's case, he actually did performance analysis of code that he wrote functionally and one that he didn't. And the code that he wrote functionally actually ended up using less memory in execution. So think about that. Furthermore, there are more intelligent ways to create objects. Okay? So Facebook created a library called Immutable. And Immutable basically allows you to create sets, maps, basically lists and objects, okay? And they do this in an intelligent way. The way that Immutable, so let's go back to what we mean by mutation, copying, and immutable structures. So if you try to modify something, right, you have a list. When you modify it, you just get the same list but modified. This is bad. Again, it's bad because another thing might be using that list and you're just changing it underneath and the other thing could get confused. So avoid mutation when you can. Copying, using maybe concat or something, or slice. What does copying do? Well, you could, for example, let's say you want to add 100 to you want to change, you have an array with 11, 5, 10, blah, 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 and you want to change that first value 11 to 100, right? What you can do is you can concatenate 100 to a slice, basically to this subarray, from 5 down to 32, and you will get an array of 100 to 32. Okay? But as you can see, you're copying all these values into a new array. Again, not a very efficient way of using resources, of using memory. Can we do something better? Can we do something more intelligently? Turns out we can. So what we could do is we can store that initial array as a tree. So forget about the red for now. Just consider this tree here. This is the same exact array where each pair of values is stored as the leaves of the array. Those then have parents, those then have parents. Okay? Then, if you want to modify this, what you do is you create another leaf of the 100 and, of course, whoever it's close to. And then you create another leaf that pairs that one with this one. And then you create another leaf that pairs this one with that one. In other words, you reuse all of this and you reuse this, right? This is known as structural sharing. You are sharing parts of the structure with another object. You can do this only if you are guaranteed that the original structure will not change. Of course, if the original structure changes, this all goes to hell, right? But if we make the assumption that the original object is going to stay the same, we can reuse parts of it in our new data structure. Kind of cool. Much better efficiency as far as memory usage, especially if your list is much larger, right? Now, there are various versions of this. It doesn't have to be 2 by 2. You could have 32 by 32 and so on. You can chunk things in various ways, but the approach is basically this, that you break up your array into parts, and then you reuse the parts when you create the new version. Now, why do we use a tree, you might ask? Well, the moment you guys think of tree, you guys should think, okay, logarithmic search, right? Super fast search, logarithmic time, where the branching factor is the log value. We could have done this using a linked list. By the way, knowledge of data structures coming back, huh? You could have done this using a linked list. But the problem with a linked list is that it requires sequential search. You have to test one, then go to the next item in the list, test that, go to the next item. So if you want to jump to index 5, you would have to go through 0, 1, 2, 3, 4, and 5. If you paired them, yes, it would double the time, but you still have O of n, effectively. O of n over 2, which is basically O of n, right? With a tree, you can do effectively binary search. You can do some intelligent things where you take the number, for example, 5, turn it into binary, And then depending on the values of binary, hash to either this way or that way, depending on if it's a 0 or a 1. And then hash your way down to this. Basically, the tree structure allows us access to the values very quickly. Now, yes, it's not as fast as a native array, which just does, memory calculations, right? You just add that index, you multiply that index times the number of slots in your array, and you jump to it or something. Yes, it's not as fast, but still logarithmic time is not bad. And again, the difference in time, guys, when you're talking about logarithmic changes, is so minor that you really don't have to worry about it. So if you're worried about all this extra copying that you're doing, you can use Immutable.js to do much more intelligent allocation of memory. I personally, and I've been building a React application, a very large one, I just do regular object.assign and concat and basically native modifications. I don't use Immutable.js, and I have had no problems with performance. So I can come to you with experience saying, like, really don't worry about it, unless you have massive arrays or you're doing something really crazy. If that's the case, consider using Immutable.js. Why is functional programming suddenly so popular? Okay, we mentioned that multi-thread programming is not something we have to worry about, right? We live in the JavaScript world. One thread. But the problem is that if you look at the processing power over time, what you'll notice is that processing power has been increasing by a lot. And this, I believe, is a logarithmic scale, so it's actually even sharper than this. But after a while, it plateaued. Why? Well, because of physics. Because there's only so many atoms you can fit on a wire. At some point, you have to do something else. You can't just keep increasing the number of things on the processor, right? I mean, at some point, you reach a limit. So what are like Intel and all these companies doing now? Well, they're adding cores. So instead of just making one CPU faster, they're just adding more of them. Okay? Well, if you have more of them, the only way to take advantage of them is to be able to execute things together, in parallel. If you're doing sequential execution, one is enough. Those of you who have written Node and have deployed it to a server know that if you deploy it on, say, a quad-core server, you have to cluster. You have to create 4 instances of your node, 1 per core. Okay, so how do we take advantage of this, say, in the browser? Well, you know that we actually have this. Web workers. Web workers are exactly this. A web worker, when you spin it up, is a thread. Now, it's not part of the JavaScript language. The language itself doesn't specify threading. It specifies just the syntax of the language. Threading is something that is given to you by the execution environment, in this case, the browser. Browsers now give you web workers. And what are web workers? Web workers are threads, but, and here's what's really interesting. The people who created web workers seem to be functional programmers. Because what they don't allow you to do is have shared mutable state. To use a web worker, you take a value and you pass it as a message to the web worker. The web worker can't change a data structure underneath you, nor can you change an object underneath it. You give it a value, it gets a copy of that value. It does whatever it wants, and then gives you a new value, a copy, that you can then use however you like. So the two threads are completely separate. And again, guys, one of the things that functional programming really gives you is this ability to write multi-threaded code, but safely, in a way that you don't have this problem of race conditions, in a way that you don't have to then create locks to try to avoid these kind of problems. Use functional programming as much as you can. For everything else, it's what you know. Thank you. Ժամանակ ունենք ասեի, թե չէ։ Շեֆ։ 5 րոպե առաջ էր։ Լավ, 5 րոպե։ Do we have questions? Հայեր են, անգլեր։ Աջան, yes sir.
It's like a little bit question, but a little bit of a suggestion as well.
Sure.
So I would add that functional programming, so in JavaScript, the language itself is not going to help you, right? So we just have to be disciplined.
Sure.
And I promise there is a question at the end. But the thing is, like in functional programming, it's the control structures themselves that allow you to express things as values. right? So like in JavaScript, the try catch is not a value. It's some kind of operation. And now with all these other opportunities to compile to JavaScript, my question for you then is like, why are you writing JavaScript? Why are you not writing ReasonML or TypeScript or other languages that make these kinds of things a first-class citizen, rather than reaching for something like Immutable.js, which the OCaml compiler is going to be doing naturally anyway?
Good question. Okay, so just to repeat so everyone understands. So there are lots of languages that will compile into JavaScript. And some of them enforce functional programming. In fact, they push you to functional programming. They give you functional programming constructs sort of natively, so you don't have to be using libraries like Immutable.js to get this kind of immutability. Is that a fair? Okay. So the question is, why am I not just using those? Why am I still writing in JavaScript? Fair point. So first of all, I'm not the only one on the team. And the problem is it's hard enough to find people who know JavaScript. Finding people who are experts in some of the languages that you mentioned, I would argue is even harder. And so one reason is just the team. Another thing is just, some of the resources that are available, I don't know, some of the support that's available in JavaScript, more of the documentation, more code examples. If you do a search on, I don't know, Stack Overflow, you're going to find way more examples and solutions for how to do things in the JavaScript because it's just so popular. It's basically, the short answer is it's more mainstream.
So if you open up a company tomorrow and it's just you?
It's just me? Yeah. I wouldn't open up a company if it's just me. I would just code myself. But the thing is, okay, even if it was just me, I would still use JavaScript, and let me explain why. Because if I opened up a company, my assumption would be that the company would grow. At some point, I would need more help. And we're back to the same problem. So I agree with you that some of the, there are JavaScript, okay. JavaScript is not the last programming language, I hope, okay? JavaScript by far is not my favorite language. JavaScript is a good language. It has some, as Douglas Crockford likes to say, it has some good parts. And those parts, I think, are awesome. It also has a lot of bad parts. It has parts where you can really trip up. There are better ways to do a lot of what we're talking about in other languages. And certainly, certain languages have strengths and certain languages have weaknesses. And our assumption is that languages will evolve and that better languages will come out over time. So absolutely, JavaScript is not the be-all, end-all. But currently, again, just because it's so mainstream and just so many resources, both programming resources and others are available for it, this is the main reason why I choose to stick with JavaScript. Is that a fair, satisfactory answer?
It's fair.
Cool.
But do you think that that's a function of being in Armenia, though?
No. Yeah, because we have the same problem in Boston. Same problem. Yeah. Cool. Other questions or concerns? 1 minute left. No, I should just shut up. Okay. Thank you so much, guys.